So for this video tutorial, what we're going to do is we want to see what happens to the kinematic equations when acceleration is equal to 0. So going back to the first intro video, we know that when acceleration is equal to 0, we have constant velocity. So what we should see for the four kinematic equations is that they reduce to the constant velocity equation here. Or in another way, we have the initial velocity equal to the final velocity. So we should see both of those things in the four kinematic equations when acceleration is equal to 0. So let's just label these equations here. So now let's see what happens to equation 1 when the acceleration is equal to 0. So we're going to set a equal to 0. So if a equals 0, the last term here goes to 0 then. So then we just have df is equal to di plus vit. So now let's just rearrange that to see if we get it into the constant velocity form here. So now we could subtract di from both sides. And now we divide both sides by t. So now these t's cancel. And then we have vi is equal to df minus di over t. And now we know that if we have constant velocity, the velocity is not changing. So what that means is the initial velocity and then the final velocity have to be equal to each other. So we have vi is equal to vf. So we could just call this one variable then. So we know vi is equal to vf, so we could just call this v. So that means that vi is equal to v. So now we have the same form as the equation for the constant velocity. So that means that equation 1 agrees with the constant velocity equation, which should be happening because we have acceleration equal to 0. Now what about equation 2? So for equation 2, if we set a equal to 0, this last term here is going to be 0. So then we just have vf squared is equal to vi squared. And now we could just square root both sides. So then we get vf is equal to vi. And that makes sense because we already discussed that if we have 0 acceleration, we have constant velocity. So the initial velocity has to be the same as the final velocity because velocity is not changing over time. So equation 2 is also valid for constant velocity. Okay, now what about equation 3? So for equation 3, we set a equals 0. So this last term is going to be 0. So then again, we have vf is equal to vi. So same as equation 2. So what about equation 4? So equation 4, we don't have acceleration in this equation, but we know that vi is equal to Vf, and we just called this variable v. So we could set Vi equal to v, and then Vf equal to v. So let's do that for equation 4. So we're going to get v plus v here, which is going to give us 2v. So then these 2's cancel. And now we want to solve for v to get in the constant velocity form. So we can just subtract di from both sides. And then we just have vt on the right-hand side. And now we'll divide both sides by t. So the t's cancel here. And then we just have v is equal to df minus di over t. So this gives us the same form as the constant velocity equation. So basically, if we set acceleration equals 0 and the kinematic equations, they all reduce to constant velocity. So they're either going to be in the form for the constant velocity equation here, or you're going to get vi is equal to vf. And then if we look at this constant acceleration equation, we know that vi is equal to vf. So if they're equal, if we subtract those two from each other, we're going to get 0 then in the numerator. So if we have a is equal to vf minus vi, we know that they're both equal to v. So we have v minus v over t. So then we get 0 for acceleration. And again, that makes sense because if we have constant velocity, the acceleration is going to have to be equal to 0.